2, 3.
Okay, cool. I think it started. Yeah, so this lecture is about planning under Vstar realizability and introducing an algorithm called TensorPlan. So you guys can probably tell this is going to be an upper bound. Anyway, for a little bit of context, what we had before was, this is very early, like I think you had it 2 or 3 lectures ago. That was this result that if you have some inaccuracy in some misspecification in the linear model of size epsilon, then you have to accept a square root d factor of blow up, where d is the dimensionality of the features. If you wanted a policy that is more optimal than that, then you'd have to take an exponential number of queries. That's the left arrow. But if you were okay with this suboptimality, then you could use g-optimal sign and approximate policy iteration and get a polynomial kind of runtime algorithm. So then we moved on to, and this is previous lecture, I guess, moved on to like, what if only oh yeah, because the previous one, every policy was realizable. And now, like, the next question is, what if only the optimal policy is realizable? And again, you have an epsilon misspecification. Yeah, so like same thing applies as before. If you want like super good suboptimality, then you still can't do it. But even if you're okay with the square root d blow up, there is a question of, you know, do you have many actions? Because if you do, then the previous lecture's lower bound applies. And if you don't, then that problem is open. And here, what we mean by many actions, because this has been defined since, like, this is like, if you have, you know, greater equal d, or like, I guess d to the 1/4, then the lower bound, exponential lower bound applies. And otherwise, the question is open. So that's kind of, you know, I guess what is smaller than d to the 1/4? You know, it's probably going to be like order 1. Like, what if you have a constant number of actions? What if you only have, not 1, because that's simple, but what if you have 2 actions, or 3, or, you know, something like that? Do you still have a, yes, Vlad?
And is this the case for the finite horizon and infinite horizon setting?
Yes, yes. And there was a question about comparing the two, which I will get to at the end. But in kind of broad terms, I think every single result I'm about to talk about applies for both. So there will be caveats at the end, which I will say there are minor differences between how the results apply, but exponentials will be exponential and polynomials will be polynomials. But I'll come back to that. Yeah, and this lecture, as was the previous one, will be talking about finite horizon, but there is no like big reason for it other than the ones that I will get to at the end of the lecture. So should work does work, in fact, for the discounted as well. Okay, so yeah, so like, okay, the question is, what if you have Q-star realizability and you have order 1 actions? And it turns out this is still an open problem today. But something that we can do is introduce V-star realizability. So like previous lecture was about Q-star realizability, where you had this sort of an assumption that the you know, that the features linearly approximate this Q-star. And now you have the same sort of assumption that the features linearly approximate V-star. And for simplicity, we say that the approximation error is 0, but it can be a little bit bigger than 0 as well. But let's just keep things simple. This like it has to be very, very small. Like it has to be like something exponentially super small. So we're not going to talk about that because that's going to be an extension. Let's just assume for now that the misspecification error is 0. So otherwise, we have the same thing as before. We have this V star, which gets an index h, which will indicate, you know, how many more steps you will have in this MDP to sum up, just like in the previous lecture. And then you get the features such that there exists a theta such that the inner products of the features in the theta will be exactly equal to V star for each state. And we also assume that this theta has like a bounded 2 norm. Let's say it's bounded by B, capital B. So that, yeah, that's just something else we add on the side, that it shouldn't be like infinitely large. There should be a bound for it. And yeah, the result that I'm going to talk about is that it turns out you can have a tractable sample complexity if you have order 1 actions. Yes, Vlad?
Yeah, sorry, one more question. I was just thinking about all this stuff right before the lecture. Is there any way we can relate these Q star to V star settings? Like,
yes, good question. And again, like I think I'll come back to this at the end, but just until then, I will say, if you think about like an MDP that has deterministic transitions, so like every time you take an action, it will get to the same state.
right.
The rewards might be stochastic, but the let's say the positions are deterministic. Then you can think, well, the V star for the action, so like the Q star for the action that you pull is exactly the V star of the next state,
Yeah.
plus the reward the expected reward that you get. So you can then translate between these two very easily, because the expected reward is kind of like easy to measure, and like, you know, then you can translate between the two. But there are, in the general case, there are other issues. So in particular, so what ends up being the problem is if you want to do TensorPlan with Q star and you don't assume that the transitions are deterministic. If you assume transitions are deterministic, then it works. If you don't assume that, then you have a problem. And the problem will be measuring the expectation where within the expectation you have a max operator. So that I will come back to that later, but that's kind of the difficulty. Csaba?
Yeah, so if people read Rich's book, he's talking about after states. So in some problems, like operations research, you have a state variable, and any transition can be decomposed into a deterministic component and a stochastic component. It's like you have your stock, and you're stocking up, like you're buying and selling products. So you have your stuff in your stock, and then you sold, and you are ordering. If you're selling or ordering, you know exactly what's going to happen to your stock. You're going to have less stuff or more stuff. And that's deterministic. After that, there is a kind of a shock that happens to the system, which is like customers coming to your shop, trying to buy things. So that's a random process. So that's like the demand, that's a random transition. So in some problems, you have this decomposition. And I suspect that maybe like this reduction that Galliot was talking about, that was applying only in the case when you have deterministic transitions, would also apply when these transitions can be decomposed into these two parts. What do you think of that?
Well, I guess the question is if you can learn enough.
Vstar would be defined for the after states. Like these are the states that result, these intermediate states that result from the deterministic component transition, after which there is a stochastic transition for which there is no role. Like the actual.
Oh, I see. Okay, so you don't actually control the. I see. Okay.
Yeah, it's an uncontrolled shock.
Yeah, I think. Yeah, and you could actually imagine. Right? Can't you like say that the if you don't want to model this shock thing, that will happen. I guess it will then. No, but I see your point. Like your action doesn't determine the stochastic part of the transition, and I think maybe in that case, it's a good question. I'd have to think a little bit more about it, but I think maybe in that case, TensorPlan would work because it learns just from this. Yeah, it takes an action and then it sees the transition and it learns from it. But yeah, let's come back to this. Maybe this should be homework because I don't actually know the answer for sure. Yeah.
If you were not around, I would definitely have said that this is just a homework.
Yeah, I don't know if I'm allowed to set homework though, so you have to say. Okay. Okay. So yeah, to move on, we're going to be in the online planning local access problem. So that means you wanna plan as you go, but you only have local access, so you can only reset to states that you've seen already, and you only see the features for things that you've seen already. Okay, and yeah, like this is the way the planner works. You might have seen this figure before. I don't know. There shouldn't be anything new here, right? Okay, so what the theorem says is that yes, go on.
Sorry, one last question. For this picture here, that input to the planner routine at the bottom, you see we have the feature matrix or the feature vector for a given state. How would that look like under Q-star realizability? Because then we get features over states and actions, but we don't know
so
the action.
In Q-star realizability, I'd say that you get like for each action you get the features. So you get like a feature matrix which can which has all the actions.
So then we assume that the MDP has to give us a feature for each of the actions at the state we're at.
Yes.
Which is kind of less ideal than this, I guess.
I mean, it's
well. I mean, this is hiding a big caveat, which is that if you only have this information, then you can't actually, without the simulator, you can't do anything because you don't have anything to identify the actions. So if you, because to identify the actions, you have to kind of try them and see what features you end up with, right? So you have to use the simulator to do this one step look ahead, and without that, you can't do anything because you don't even know which action is what. I can really easily mix up the actions and you don't know what's what. Whereas with the Q-star, if you're given the features for all the actions, then theoretically you do get information about every single action, and you could just decide as you go. So with that formulation, it is possible to do the global planning where you have to output a policy that really only acts on the things that you receive. Whereas in this formulation, there's really nothing, like you can't do the global planning because you will always have to do the one step look ahead. So I think there's a good reason why I think if you didn't give the features to the Q-star, you'd have to like try state action pairs to get the features. You just have to, you'd just be stuck with doing online planning. And it doesn't seem to be buying you any advantages. But yeah, I guess you could define things that way. But yeah, does that make sense?
Yeah, that's great.
Csaba, did you want to add something to that?
Absolutely not.
Okay, cool. Okay, I will dart on because it's like 20 minutes in, so I need to get to the juicy bits. This is the theorem that you have like some number of actions and some horizon, and for any delta, there exists this planner with the following properties: that the planner is delta sound, and as long as the assumption of Vstar realizability holds, and that the number of queries is bounded by this. Now, the important bit here is that A is in the exponent, and that's kind of the where you should say, oh yeah, like is this still a polynomial? It is a polynomial of this quantity, right? But this itself, like A has to be small for this to be tractable. So yeah, that's basically what this does. And notice also that this is bounding the number of calls and not the computational complexity. So in fact, the computational complexity, like it's probably going to be very hard, but we're only looking at the query complexity here, which is the number of times you have to call the planner. Okay, so this is the theorem that we're about to prove today, if not fully, but yeah, you go on.
I wanted to ask why would the computational complexity be hard?
So the algorithm will internally have to solve an optimization problem over a kind of seemingly really non-convex set of things. So that it's just hard to solve that computational problem, within the loop. So the problem will be to choose the optimistic theta if you're ahead. But I'll get to that. Yeah.
Maybe related question, but Do we know whether this is necessarily a computationally hard problem?
No, I don't think we know that. So it's an open problem. You might be able to find that there's a way to like solve it or approximately solve it in polynomial time, or you might find that there is a different version of a different algorithm that like doesn't even need to solve this problem. So yeah, this is completely open if you want to
Or
work on something.
maybe it is hard. Who knows?
Yeah. It could be hard.
So
Or
another
not. Yeah. So okay. And where does TensorPlan fit in? So it, if you've got this a similar kind of chart as before, so Vstar is realizable. If epsilon is large, then you have a problem. If you have many actions, then you have a problem. But if not, then what this will say is if you care about runtime, if you don't care about runtime, but only query cost, then here's an algorithm. And otherwise the question is open. So this is just a sum of what we've been talking about. And now finally getting to the algorithm, what is TensorPlan? So, okay, what TensorPlan does is, well, I mean, the assumption tells it that there is a theta for which Vstar is realizable. And so what it will do is it will keep a set of feasible, possible thetas that might still be this theta star or this theta that for which the inner product will be Vstar. I will call that theta star. I hope that, but maybe call it, actually, we should call it theta plus because it's going to be a bit more general than that. In fact, it turns out for any deterministic policy, it can compete with that deterministic policy as long as the policy is realizable with the features. So the easy version of this is to say that Vstar is realizable, and then it can get an algorithm that it can get a policy that will be almost as good as the optimal policy. Right. Okay. So what it will do is it will keep a set of feasible thetas that might still be the solution, and then at the beginning of each iteration, it will keep iterating, and at every it's doing this optimism where at the beginning of each iteration it chooses the theta that promises you the best policy, and it will say, I'm going to test this theta. Either this theta gives me the rewards that I thought it would give me, and then it's great because like nothing better would have existed in my set, so I'm done. Or if I see some discrepancy, then I will shrink my set, right? And I'll shrink my set and I'll start a new iteration. So I'll keep iterating and the set will shrink, and at some point I'll return something. And there's two questions. One, how many times do I have to shrink my set before it will definitely return with something? So like, does this run forever? Kind of question. And then the second question is, does it, when it returns, does it return something good? Does it return this like delta optimal policy? So like this is roughly what we're going to talk about. So just to explore it with more detail. So initially it chooses this like optimistic policy, and it's really just taking the argmax of the star state feature and inner product with the theta across the like feasible solution range, which is this shaded green region that it maintains. And it chooses this theta plus, and then provided that this theta star is an element of this green shaded region, this will ensure that the value that the theta plus promises, which we're just going to say is this, it's defined here, is just the inner product, is going to be at least as large as the Vstar. So this means it promises us at least as large a value as Vstar, and then now we're going to check if it really delivers on this promise. And if it delivers, then we return, and then we're sound. And if it doesn't, then we shrink the region. Okay. So how do we check if it delivers on this promise? So once this is within the iteration, what we do is we have this theta plus, and we have an associated policy, and we just check that policy. We unroll it a bunch of times from the state, and we check if the value that we measure is kind of what was promised to us. And don't even worry about this, because we'll see that the 1 and the 2 will be the same, but it also checks for consistency, some sort of a consistency. But before we talk about that, let's define what this policy is. So for each theta plus, there is a policy that it will keep trying. And what is this policy? It's defined here. So it will choose an action A in a state S such that this kind of consistency equation holds. And this consistency equation says that the value that is promised to us from state S by theta is exactly the reward plus the next state value promised by theta. So it chooses an action for which, if you just locally look at, the reward that you get with the action plus next state value promised to us by this theta is exactly the same as the value promised to us by this theta in the current state. So that's the consistency equation. The policy will try to find, so a policy for a theta will try to find an action that is consistent according to that theta. And notice that we don't, yes?
I was wondering, why do we check the first one here? I was thinking it would be adequate to check the consistency.
No, the reason why, yes, it is adequate, because actually it turns out that like the two checks are the same, but it's just so to give a more convincing account of why this will return an optimal policy. We say that by checking the two, by checking the consistency, you basically also checked the value guarantee, right? And we'll talk about why that holds later. So in effect, you're only checking that star holds, but actually by checking that star holds, you also check this. Does that make sense? It is because if these two hold, so I guess if this doesn't hold, then this also won't hold for one of the steps, and vice versa. If this holds for all the steps, then this will hold as well. Yeah. I guess two implies one is what I should say here. Okay, so and notice how we check for consistency. There was a note in the notes. There was a little remark that says you could also choose max action of this, right? And why isn't that being done? And wouldn't that be better? And I guess the answer to that is it could work just as well. I think it will work if you have Vstar realizability, right? But still, I mean, I haven't entirely thought it through, but I think it should work. However, and this is something I was talking about before, just like a couple of minutes ago, but I think I was being quite confusing. The way it is, if you only check for consistency, then TensorPlan works also when the optimal Vstar is not realizable, but some other V pi is realizable for a policy pi that is deterministic. Then you might not, you might not always have this max thing be consistent, but you will have, for the one that's realizable, you will find the consistency and you will be able to be at least as good as that policy. So it's just a little bit stronger theorem by checking for consistency rather than taking the max. So it turns out you don't necessarily want to be optimistic while unrolling the policy, but you do want to be optimistic when you first choose the theta plus at the beginning. Okay, I think that's was this all clear from this side?
Except for the last sentence, where you said that for rolling out, you don't want to be optimistic. I think you wanted to say you don't even want to consider choosing the argmax, like the greedy action when rolling out.
Yes, that is exactly what I meant.
Although, if you find one, you can always go with that. But if you find something else that so the max, it would make sense, right, to order the actions based on one step look ahead. That would be the practical thing to do, and go with the action that promises the most value. And if that is not consistent, then go with the one below it, and basically try to satisfy this equality, or you go directly and try to satisfy this equality. Or maybe the other way to think about it is that The left-hand side is given to you. The right-hand side you can compute. And if there is an action that matches, of course, you're going to talk about that. It's an approximate match, right? Like in an interval, there is a match. Then you can go with the action which satisfies this match up to this approximation that you're hiding here, but it will be there.
Yeah.
So somehow filter out the actions which don't have a chance, and amongst the actions that do have a chance of satisfying this equality, given the precision with which you were measuring things, choose the one which is the best.
Yes, yes, but you know, this precision will be tiny. So give it, you know, around those.
Yeah,
if you're
it's like
strict,
it almost makes no difference of just
Yeah.
saying that. Choose any.
yeah, but you might as well choose the best one. So yeah.
Yeah.
Okay. Cool. I hope this was clear. Yeah. But to go on to talk about how this works and why it stops and when it stops and you know, if it stops well, if it stops with a good policy, we introduced this thing that I think, Chaba, you call a discriminator, and it's this delta, and it's going to be the sum. I think this was a typo in the notes. It's a sum of the reward plus the expected next feature vector inner producted with theta minus the feature vector inner producted with theta now. So this is it is very similar to this consistency thing. In fact, if you, yeah, like it's the right-hand side minus the left-hand side, and that's the discriminator. And okay, so basically you want to, when you're unrolling the policy, you want to choose an action for which this is 0. Okay, so we're going to make this huge simplifying assumption, and because I think this whole thing is split into 2 lectures, right? So like the simplifying assumption is that you can measure the delta exactly, right? And so we're going to talk about like what if you can't measure it exactly, and if we have time, I mean, I guess maybe even in this lecture, but for now, let's just say we can measure this exactly. Of course, we can only measure it approximately, but that will be good enough. And I think everything I talk about, the intuition of it will apply, even if you have a bit of an error. Okay, so let's just say we can measure these. And then what we want to find is a consistent action. We want to see if there is a consistent action, otherwise the check fails. So to say that there is a delta that is 0 is the same as to say that the product of the deltas is 0. There is a delta that is 0 if and only if the product of all these deltas are 0, the product across actions. So the consistency check goes through if this product is 0. And there must be one consistent action, and you can keep, you know, going with that. It's an equivalence, so we didn't change anything here so far. And then the next step is to say that we can actually this discriminator delta, we can write it as an inner product, right? And because what is it? This is like, it's got like d-dimensional inner products, and it's got a scalar. So you can say this notation is just concatenation. So you can say that you concatenate the reward. It's kind of confusing, I get it, because last time the concatenation was like this. But anyway, now it's an overline. So you concatenate the reward with the feature difference, and then you inner product it with like the concatenation of 1 and theta. And that is a d+1 dimensional inner product that will give you the discriminator. And then if you want to talk about the product of these discriminators, then we use this kind of thing, which is to say that the product of inner products is the inner product of the tensor products, right? So you have the x's, you have the y's, and the product of the inner products of these xy's is just one inner product of the tensor products of the left-hand sides, the x's, and the tensor product of all the right-hand side y's. So that's a nice little way to think about this, because what you have now is you can basically write the whole thing as one inner product, and then we have this whole like product of deltas is equivalent to this huge inner product, where you have like inner product, tensor products of the left hand side and tensor products on the right hand side, and this whole inner product needs to be 0 for the consistency to hold. And so what is this? This is you can think of it. Okay, so what is it then? Is it clear what a tensor product is? Like it's just you know, if you have like 2 vectors and you take an outer product and you get a matrix, it's kind of like that, but you can generalize it to like more vectors. You can get a lot of different vectors and you can outer product them, and that's kind of the tensor product. And so this is going to be this is going to give you a tensor that is of dimensionality d plus 1 x d plus 1 x and so on and so forth a times, right? Because you took an a-wise tensor product. So that's this. And then the same thing here, you know. And you can actually treat this as like a huge vector, right? Like the same way you can take an n by n matrix and say that this is an n squared vector. You can say that this whole thing here lives in R to the d plus 1 to the a. And so let's just make a shorthand like k. Let's let this be the quantity d plus 1 to the a. And then we can say that this is a k-dimensional vector. And so is, you know, this one. And you take an inner product between these two. And it's 0, right? Like that's what you learned. Like, you know, it has to be 0 if theta was correct, right? Okay, so what we did is we just blew like this d plus 1 dimensional thing. We blew it up to like d plus 1 to the a dimensions. And so it will become very clear, I think, hopefully, why we did all this. Because now we have this linear algebra kind of business, and things will just be very simple from here. What we did is we reduced the consistency check to this. And we know that the good theta that we're looking for satisfies this, right? So what we do is we call this left-hand side D and the right-hand side F of the inner product. And then we say that, you know, like what TensorPlan does is it basically collects data of this D form, right? And it doesn't know what F is. It wants to find F. And so whenever it detects an inconsistency, it knows that for the F that it wants to find, this inner product has to be 0, right? Trevor?
Yeah, just like it knows the functional form of F. It just doesn't know the theta that would go into it. So
Yes.
altogether it doesn't know F, but if we forget about the functional form, you can just like look at it as like you just have this huge tensor or multidimensional matrix that you're trying to find. And then that's what you're talking about, right?
Yes.
Okay.
So yeah, it doesn't know theta, therefore it doesn't know F of theta, but it knows the functional form of F. But I guess, okay, so what TensorPlan does is it will collect the data on the left side of the inner products, and it will shrink the hypothesis set, which is going to be the set of all possible F thetas for which theta might still be feasible. So it's this big, gigantic dimensional. Actually, no, it's in the theta dimensional in this case. So okay, it's in the d-dimensional set. So this is the set of thetas that are plausible, and it chooses it such that the theta should come from an L2 bowl of size b. That is assumption. So like the L2 of it is at most b, but also the F of theta. So like this big dimensional thing that I was talking about, inner producted with the big vectors that it measured so far, has to be 0 for all the different interactions, different times when it saw an inconsistency. So like, you know, you basically shrink the hypothesis set such that your F of thetas will be orthogonal to the x's that you collected. Does that make sense? Cool. Okay. So why is this great? This is great because you have a very simple argument here. Like, what is the dimensionality of the F of thetas? Right? Like, what is the F of thetas that you allow? every time you find an inconsistency, you like say that there needs to be one more orthogonality condition that needs to hold. So like you have a linear space that is initially k dimensional, and you say like you restrict it such that the inner product with like one thing is 0, then it will become k minus 1 dimensional, right? And so on and so forth. So like every time, so you keep restricting it, and it's a real restriction, right? Like it's not like everything was already orthogonal to this, because then you wouldn't have had the inconsistency. So you see an inconsistency, and then when you add that, you reduce the dimensionality of the f theta space by 1. And initially it was k dimensional. So it makes sense that this will only go on for like at most k steps. In fact, k minus 1. But yes, that is how you get like a bound on how many inconsistencies you can detect. And because k is this huge dimensional thing, that is why you will get the a in the exponent.
Wait, why is this k minus 1?
Well, at the
If k
like
equals
how many
1,
times can you detect
like you have a
inconsistency?
line, and then you still have to get a point or something.
Yes, but if you have a line, you can't see an inconsistency anymore, because that would get you 0, right? Like then.
That's point. A single point.
Sure, but okay. So I guess what I'm saying is like if you had one more step of inconsistency, then you would only accept 0 as the solution. So if theta is anything but just 0, and if it was, then like then I think everything would give you the same. Yeah, it's a little bit confusing. I'd have to think about it, but basically I guess this whole line thing. So
It's like there is this affine subspace or something, so it's a little bit, yeah, shifted with this theta, and like when you reach the one-dimensional case, you're basically done because of other
yes,
reasons.
you must be right. I mean, I am confused. I have to agree. Like, why is it that you have a line?
Okay, Kushagra was asking some question.
Yeah,
yeah, go
so
ahead.
if k is 1, then a must be 0, right? Which doesn't really make sense.
If k is 1, then a must be 0. But what?
Oh,
Did I
the
say that
number of
k is
actions,
1?
but okay, we are just abstractly trying to reason
Oh.
about that here.
Oh, I think, yeah, like, I guess what we were talking about is like, as you reduce, I don't know if this is what we were talking about, but I think it was like, as you reduce the dimensionality of your f theta, for the theta that are in this big theta set, like as you reduce the hypothesis set, like what will be the dimensionality of this? And then when it reaches 1, it's not like k equals 1. Like k equals still like that huge thing, but you've been playing for a while and you reduced it. So like when it reaches 1, it can't go any further because it can't get to 0 dimension, right? And at that point, like you will have to, yeah. At that point, it's unclear because you still have a line. Why you want to have? I would need to think about this. Maybe we'll come back to this at the end.
Okay.
Yeah, but yeah, good job confusing me here. Okay. I guess there's not much left. There's like the soundness, and yeah, like maybe we'll talk about a little bit of other stuff as well. But yeah, like okay, so you'll only run for k steps. So that's the first part that we're done with. That like you only have like this many, up to k many inconsistencies, but the question is like when TensorPlan returns, why would it return with a good policy? And that's basically what I alluded to before by saying that 2 implies 1. So like if you have consistency that always holds, which is when TensorPlan returns, then you necessarily also have that the value is achieved. And so why is this the case? Because obviously, like if the value is achieved, then you're golden because you chose optimistically. So and this is just a bunch of Hoeffding's inequalities, because like, okay, so when TensorPlan returns, that means it hasn't found any inconsistencies, and it has done a bunch of unrolls of the policy, like m different unrolls of the policy, and it hasn't for a single time detected any inconsistencies. Then you can write up the things that it has seen, like I think I is, what is I? I is a rollout, so it goes from 1 to m, and t is the trajectory, so it goes from like 1 to h. And so you see that like it has observed that these are all kind of equal, and then you can just say that like, okay, so what is the value of the policy? Well, it's kind of roughly the average that you measure minus some error term because of Hoeffding. So that's the first line, and then you can say, well, because this equality holds, like I can replace this with this. And this, this holds because there was no inconsistency detected. So like I can replace it with this. That's the second line. And in the third line, I say that the expected next state value is kind of close to this. So I guess the expectation of, so what do we do here?
Conditional expectation of this vt plus 1 expression given everything up to t is the same as the inner product over there, right?
Right. Okay, so these are for specific s's that you have observed, whereas this is like an expectation here, right? So you can say that like the difference between the two will be like these zero mean kind of random variables, and you can do a Hoeffding on that. Okay, cool. So it's basically the same Hoeffding, and then you've got the result that your initial value is kind of close to the one that is like promised by theta plus. Okay. Yeah, so that's because like no correct hypothesis is ever eliminated. That is a very important part of it. Therefore, with the optimism, you get that that there is soundness, because this maximum will include the set, will include the correct hypothesis as well. Yes.
I quickly wanted to ask, how is the B coming from in the last result?
Yeah. So this could be H as well, but the reason why it's B, I mean, it depends on how you want to bound the the range of these, right? Or should I say the range of these, right? Like you could say the values range is like capital B, because the theta's range is capital B, right? So and the feature, I don't even know if we had a bound on the features range, but I think it should just be capital H. I mean, maybe Trevor, you can chime in. Did we not?
I don't know why.
It should be. I think it should be.
Wait. So B was the bound on the parameter vector, though, right? Like features bounded by 1, and like these are inner products. It's like, okay, you can reduce everything in terms of B. Maybe B is smaller. Maybe you could take the minimum of B and H.
Yeah, but
I'm
okay. So what
looking for a missing H factor. Should multiply that because we are summing up. Oh, the sum is also very interesting. It goes from t equals 0 to t minus 1. Wow. Okay.
H
so I
minus
guess that
1
should be H minus 1, and then maybe that should multiply this B by a factor of H.
Yeah, but okay, but what you could do is you could like clip the inner product, right? Like you can say
You're
like
telescoping, and okay, like the whole.
Oh yeah, I didn't say about the telescoping, but obviously, yeah, you're like subtracting the VT plus 1s and adding the VTs. So what you'll have is you'll have the V0, and you'll have a minus V capital H plus 1.
Right.
But whatever this is 0, right? Because you have a this is all
but
0.
Okay, so okay, so you can clip stuff. I don't know. Okay, so either there is an extra age or there is no extra age.
Right. Yeah,
If
like
we are doing things in a very simple way, then maybe there should be an extra age, but maybe you can save that by being more clever.
yeah, and the B, I think you can save the B by clipping, no? Like you say that the inner product, you only care about it
Right.
if it's between 0 and h. You'll clip it.
Okay. Look, well, okay. So maybe you can clip the value function. That's what you're saying.
Yes.
Right. You would clip the value functions to be between 0 and h, and then the magnitude of B doesn't, like the magnitude of parameter vector doesn't matter. So that's maybe a little bit better.
Yes.
Because
I
then
wonder how we did it. I don't remember how we did it actually in the paper, but I guess no. I think we made the mistake of having the capital H turn up in the polynomial, and it really shouldn't. The capital B turn up in the polynomial, and it really shouldn't. It should only turn up in the logarithmic factors. So that's something that like.
Yeah, the algorithm needs to construct these sets, and for that it needs B. Does it?
Yeah, it does need to know B, but the sample complexity should ideally only depend logarithmically on.
So it's kind of like if you want to set up the algorithm such that it takes as input epsilon data and it has to output an epsilon data policy or whatnot. So Federal probability at most data, and it has to output an epsilon optimal policy. Then it needs to know B. But if the algorithm would be set up in an anytime fashion that, like, okay, as it goes, it kind of doubles the budget that it uses, then you could get away with a bound. Then the result would say that as soon as the budget is large enough, and the budget doesn't have to be large compared to just D and H and 1 over epsilon and log 1 over data, and B is not included, then the algorithm will start to output good policies. Then there would be no B dependence at all, neither in the algorithm nor in the result. That would be the most ideal result, maybe, and closer to what people would do anyways, because, well, you have some budget, you're running your algorithm, you look at the output, you're not happy, then you're increasing the budget, you're still running it, and so on and so forth, right?
Yeah. And yeah, I mean, there is the other problem, which I think here you can get away with just using H and you don't need to use B.
Yeah.
But the other problem is when you're measuring, which we glossed over because we assumed that you can measure this exactly. But when you're measuring these vectors, you don't yet know what you're going to inner product it with. So you want to measure it and then save it. So you want to measure like a really accurate vector in the theta space. So that's why there's the B coming in. But whatever. I think if you're very careful, like you might
could flip there too, right?
Yeah, but like how
because the actual value
measure...
function is between 0 and h, so it's like,
yeah, but how would you measure the vector, right? Like you want to measure a vector and save it, and then ensure that anything you're going to inner product it with will have some bounded error.
sure, you're still measuring whatever you were measuring with. The test that you're running is slightly different because it involves clipping to see whether the discriminant was approximately 0 or not. You have a test there. Maybe you change how.
No, I think I agree that part can be done. What I'm a little bit concerned about is when you want to ensure that this delta is very accurately measured. That like you want to make sure that these that you add, they will actually be for the right theta, they will actually be close to 0. And to ensure that, you kind of want to bound the... Okay, maybe it's all clipping. Maybe it's all just clipping. I will have to look into
for the
this.
correct theta, the clipping doesn't do anything.
Yes.
So anyways, maybe another homework?
Yeah, it's
piling up.
Because
piling up.
it is piling up. Do let me know if this is solved, if you can get rid of the B. Yeah. Okay. I mean, you'll need it in the logarithm, but yeah. Anyway, So this is why you have the soundness, and then I guess like I think this will be next lecture, right? Like, so what happens if you can't measure this delta, this discriminator exactly? Because you can't. I mean, this whole thing so far was all nice, but you can't measure it exactly. So you can't say like exact orthogonality, and then your dimensionality of f theta is, so like, yeah, like your dimensionality of this like f theta, where like theta is from your hypothesis set, reduces by 1 every time. You can't say this because you don't have exact orthogonality if you don't measure the delta perfectly fine, perfectly well. So like, how do we get around this? So you only have like noisy measurements. So you can do noisy measurements by doing a lot of different, like, you know, like you call the same transition a billion times, and you'll have a pretty good idea of what the what the expectation is on the reward as well as the next state vector. So if you only have noisy stuff, then you have to use something like the eluder dimension, which is kind of a generalization of this dimension argument, right? Like this dimension argument is like, how long of a sequence can you make such that like you show like orthogonal stuff that wasn't orthogonal before, you know? And it's in linear algebra land, this is like exactly the dimension of the space that you started with. But if you have like inaccurate measurements, then like you'll have a very similar kind of argument that works for that, but works for this fuzzy kind of noisy version of it. And that's called a eluder dimension. And so I think that will be next lecture. Yeah, I don't know if I should say anything more about that.
No, you're good. Are you doing the next lecture too?
I mean, I don't know. I don't know. I haven't seen the notes of them, so I don't know what it exactly contains. If it's just about the eluder stuff, I mean, it's pretty fun. I could even say it now, but yeah, I don't know. We only have half an hour left, right? Or 20 minutes?
Yeah, we should 20 minutes only.
Yeah. Okay, a couple of open questions, and then the questions from the Slack. So open question is like, what if you have TensorPlan with Vstar realizability and stochastic transition, stochastic reward, everything stochastic? We talked about it at the beginning, and the problem will be like, you know, you kind of have a max operator inside an expectation. Here, you might have a max operator of choosing the max action, but when you take expectations, when you measure the delta, you know, you can just kind of do a lot of measurements and take averages. Whereas if you have Q star with stochastic transitions, then you have this problem of measuring an expectation of something that has a max inside. So this is kind of a problematic thing. Let me know if you can get around this, because this is an open problem still. And there's also the open problem of the computational question. You know, this setting, but can you make it computationally efficient? And yeah, so yeah, also like what if you have like TensorPlan with order D actions? And this one, so like does TensorPlan work with order D actions? And we do know that if you're in the Q star case, then it won't work, right? Actually, I think I should cross this off, because we do know in the Vstar case as well that it won't work, don't we? Because for the Q star we didn't use. No, never mind this one. I think this one isn't open actually, because if you have a Vstar realizability problem, then you could apply the same lower bound as what we talked about last time. With the kind of usual translation of Vstar Q star in case of deterministic transitions. Okay, so I guess the only thing that's left is to talk about this. I think there's only this one question, which was to talk about like the difference between the infinite horizon and the finite horizon, and like why we even bother with the finite horizon if we then need the notational like complexity of dealing with the subscript h. Yeah,
usually the way I do this is I ask the person asking the question on chat
Oh,
to ask the question in person.
yeah. Let's hear the question.
Yeah, let's hear the question. Human?
Yeah. So last time you said that the lower bound could be translated to the infinite horizon, and I was wondering, does that also apply for TensorPlan? Does the result of TensorPlan also applied in infinite horizon settings? And if yes, and of course you have already answered, it will be applied. So why we just use infinite horizon setting and get rid of the subscript h?
Yes, it's a very good question. I really like this question. Okay, so I actually want to say a couple of things about this. One is that you do have if you have a finite horizon thing, you have to use the subscript h, which might be a bit like extra subscript, like whatever notationally harder. But I think conceptually it might be easier because now you don't have infinite sums. And at least for me personally, when I think about like finite horizon, I sometimes find it conceptually simpler. But there is more to it. I mean, usually you can convert the results between the two, because if you have a discounted problem, like you can usually come up with the effective horizon, which is like some capital H gamma that like is a function of gamma is in the subscript, which will have a rule that is kind of like the capital H in the finite horizon case, in that after this many steps, it doesn't really matter what you do, because after this many steps, you know, you will be discounted so heavily that it doesn't really matter what you do after that. And you can set this such that, you know, any possible payout after this many steps will be less than some small epsilon. So you can usually translate between the two settings using this kind of equivalence between the capital H's, but there are some minor differences sometimes. So for example, in the TensorPlan case, the reason why I think it is simpler to introduce it first with the finite horizon and only later talk about infinite horizon is because actually if you do this truncation, because what the translation will do is like, when you want to talk about the discounted case, you will have to like truncate I say like you just truncate the unrolls after this many steps. But when you do that, then then what you measure isn't exactly going to be so like what you measure is like sum of discounted rewards isn't exactly the value, but it's very close to it, but not exactly it. There's a little bit of a discrepancy. And so first we proved everything with kind of like if things are exactly equal, and then we said, oh, let's extend this. What if they're not exactly equal? And then we can actually slot in the discounted case. And I guess it just makes sense to build it up this way. So like in this case, starting with finite horizon was the simplest kind of setting, and then we extended from there, which make sense as a way to build this up. So I think that's why we do the finite horizon in the TensorPlan. And there's another reason, and I think a better one for why we do it in the previous the lower bound, the previous lecture's lower bound, because actually if you use the previous lecture's lower bound for the discounted case, then, and I didn't say this, but the result will actually be like you know, that the lower bound will be that you need at least exponential in d number of steps. Whereas if you have a capital H finite state, finite horizon thing, then you have like x of like min of d and h, right? So it's actually a stronger result you can get with the discounted setting, but it is, I think, an easier problem to solve, right? Because if you have a discounted setting in the lower bound case, then you never have to give that final reward that makes the Q star exactly equal, you know, the payout. So you never have to, like, I think a lot of the complexity of doing that lower bound was like, to get to the final level, you have to now give a reward. So I think it's harder to make a lower bound work for the finite horizon case than for the discounted case. And so that is, I guess, maybe why it makes sense to start from the finite horizon state and say, oh, by the way, you can extend this for the infinite horizon. And by the way, you get a slightly better bound as well with it. But I do take your point. It is a bit confusing to have like two different kind of notations. I also hate it. But yeah, sometimes there are some minor differences which mean that this translation between the two settings isn't exactly as smooth as you would hope. And then you want to start with the one that's going to give you a stronger result, or the one that's going to give you like an easier kind of first thing, and then you go into the other. But in both cases, like they translate between each other. So I don't know if I gave a good enough answer to this.
Yeah, thank you for the explanation. Yeah, I found that maybe it's really just like start with the simple case would be like if there's no extra trouble in the simple setting, that would be great to start with and explaining things.
Yes.
Yeah.
So
And
like in the case, yep.
yeah, and I'm just asking to ask the transferability of these two settings. Yeah, and it turns out most of the time they can be translated to each other.
Mm-hmm. Yes. Yes. Was that a question?
Yeah, I think you have addressed it.
I guess,
Yes.
like,
Yes. I have.
to make this very precise, are there any cases that we know of where there is some striking difference? So we have actually three settings, right? The infinite horizon, undiscounted, discounted, finite horizon.
The infinite undiscounted is referring to average reward.
No, it's just like total reward, but somehow you have a nice enough problem such that the total reward is always, or the values are always well defined. So all policies are proper, for example, no matter what you do. You reach terminating state or the optimal policy. Like the values, you can't get positive infinity as a value or something like that.
I have a question regarding the setting. Could you, in this setting, have a policy that is like it takes infinitely long steps to reach the optimal reward? Like, what if the optimal reward is 1, but there's a policy that like reaches it after like infinitely long steps?
I mean, I don't know what it means to reach something after infinitely many steps.
Okay, I guess what I'm wondering about is, would it be allowed for this total reward setting to say that
Expected time to reach, maybe?
no, I mean, well, maybe, but also like I think to make it more precise, can you have an action that does nothing in this?
What does it mean to do nothing?
So you stay in the same
Stay in place?
stay in the same state and you don't get a reward.
Sure.
Okay, so then I guess I'm like disrupting this whole question, but I think in that case that's a weird setting in that you could have a policy that never reduces the Q star or the V star, like never makes a mistake, but also kind of never does anything. So that's kind of a special property of this setting, because you can't have this property in any of the other settings.
What can you explain? So you're thinking about a state where you have the option to stay put?
Yes. Like if you have an MDP, which you know, like does everything the same way as your normal MDP, but allows you to stay put and not get a reward, then in this setting there is a policy that says like I'm just gonna stay put forever, and
But then it doesn't ever incur a reward because
it doesn't
never
ever incur a
decides to
reward.
go.
but at the same time, it doesn't ever incur if you talk about like one-step regrets, which is like, you know, I guess Q star of state and what the policy chooses in the state minus V star of the state. If you talk about like this you call this like your one-step regret, then the sum across the time steps will still be zero. So like its value will be zero, but the sum of its regrets will also be zero. Is that
Are you
not
sure
weird?
about this? It doesn't seem to be the case to me. Because it's a stationary policy, right? Like if it stays put, then it stays put forever, and it's never going to incur any. So, oh, you're saying Q star. Okay, so
Yeah.
that means now take this action, but after this, I'm acting optimally.
Yeah,
Like the Q star is the same as the V star, and you have suboptimal actions, and yeah, you have suboptimal actions, and the Q star value is the same as the optimal actions V star value.
Fun so what I'm saying is it never took a suboptimal action, right? It's the policy's value is zero, but it never took a suboptimal action.
So basically, you are saying Q star, like being greedy on Q star is not a sufficient condition anymore.
Yes.
For optimality.
Mm-hmm.
Okay. We're on the same page.
Yeah, and this is weird, isn't it? It's kind of interesting.
Kind of leads to trouble, right? You can see that, like, if you are only trying to estimate Q star, like, what the heck? You somehow are thinking everything's good and everything's not good. Yeah. But it's like I was thinking about the hypercube example, which is another nice example where you know, like you have a hypercube in the d-dimensional space, and whenever you can make transitions, and then you're starting, like you want to get to some corner that will be the rewarding corner. All the other corners of the hypercube are non-rewarding. The wave functions are going to be linear just by representing the hypercube corners using this binary encoding, right? Because it's the number of, like, okay, how is it? No. Okay, so it's cost-based. Like it's a completely different problem. Sorry. It's like every transition costs you 1. Once you get to the target, you can stay put, and then you receive 0. You can stay put at any state, but if you're moving between the states, you're receiving a cost. But okay, so if you stay put at any other state than the target, you still receive a cost. And you want to find this state amongst the corners of the hypercube. But if you stay put, then you're not going to incur any cost in the future. It's total cost. And now, in this setting, everything is bad again, like for linear function approximation. It's just like the needle in a haystack, right? Like you receive no information if you're starting at any corner. Everything looks the same. It's like you just like, can I stay? Yes, you can stay. Do I receive a unit cost? Yes, you do. Can I move from this corner to the next? Yeah. Do I receive a unit cost? Yes. Like everything looks the same until you find that single corner where you find that if I stay put, then I don't receive a reward. But you never receive any further information, and you can represent the value function of this linearly, right?
Yeah.
And
because
so
it will just be like
the undiscounted setting, a counterexample to that features and this linear side information just doesn't have. So I brought up this because, trying to get rid of the subscript, you might shift to this undiscounted total cost or total reward setting. But then, okay, like there is the weirdness that Galiad mentioned, there is the weirdness that I mentioned. So it's like, It's a minefield. It's fun though. Not many people are looking at it. Oh, I guess like in the tabular case, people are looking at it, but not for the featurized case. Okay. All right.
If we have no more questions, I have one last quick question related to this definition of online and global planner. So for the global planner, we kind of, I guess we requested it has to be able to output an action for any possible state. And then for the online planner, we asked that it needs to output an action for the current state it's at. And then in like, for the simulators, we have these like local, online, and global. Is there like a similar notion of a local planner? Because I know you changed the name from local to online, and then I was thinking whether there's actually a local planner. Like, what would that definition look like? Is that, do we like request that it outputs actions for all states it's seen in the past at any point or something?
Yeah, I don't know. I guess
Not
like
even useful.
there are two aspects to the problem. What interface the simulator provides with which you can talk to it. There are like 3 choices there that we identified, and what the planner needs to return, what the guarantees there are, and we identified 2 cases. One called online. Now I call the other one offline. But I'm not sure about like you want some like you want to add something to this?
Well, I was just thinking about the notation for simulators. I was like, there's the online one, which is kind of similar to like if we can only query at the current state, like we can take an action and then it gives us the next state. There's like the global simulator kind of that you can query at any state in action. Then there's the local one where you can query at any past states and actions. Then maybe we have a local planner in which we request that it outputs an action for any possible previously visited state. I don't know if that's useful. I just like was thinking about the
So I
name
think
change.
like we are trying to just keep the definitions that seem to have some immediate use.
Yeah. Yeah,
And,
okay.
and
I
from
didn't know
this perspective, like the requirement that you output a policy that works is something people might think could be useful to have, right? Because then you can ditch the simulator and you summarize everything that is there to learn about this MDP in your weight vector or whatnot, and then you can just go. So that's like offline planning, or previously called global planning.
Mhm.
And then the online planning is that we allow more, and we have seen in the past that there is a separation between this requirement in some settings, like the tabular setting. And so we expect that online planning generally is easier because it's like you don't have to know how to act everywhere. You only have to know how to act at the current state. And then lo and behold, we saw that that's an easier problem. And so that's the reason to talk about online planning, because maybe sometimes it's just like too much to ask for this offline planning. As we saw, like there are cases where it's too much to ask for that. And then you can still do something. So that's good. You're not stuck. But then, okay, how could you do even less? I don't know. Do you want to do more or something in between? I don't know.
Yeah, I don't know. I was just thinking about the naming.
Okay. Yeah, well, yeah, if you have any suggestions for the naming.
Oh no, I think it's fine. I was just wondering whether there was a local planner and then we moved to online planner, because what we actually had was an online planner and the local planner previously wasn't a good naming for it. Yeah.
Yeah, I think that is the case, because I think we did call it local planner, but we weren't sure if that meant local access. to the features, or did it mean what we call the online planner, which is, and I'm sure this must be very confusing to listen to, but
Well, I'm planning
but
to add a little table like 2 by 3, and then like, okay, it's stupid a bit, but like, because what do I put in the table? I don't know, but like there is really this 2 by 3 thing.
Yeah.
yeah, no, when you explain it to me with the 2 by 3, that makes sense. But yeah,
Right, and
because
then
I
maybe
think
you can just remind me for TensorPlan we have local planning again, or online planning now, right?
yes,
And the motivation for that was that we couldn't do this global planning under Vstar realizability anymore.
yes, because you have to, like, you don't get any information on the actions themselves and their identities. So anything you learn, I can scramble up the actions, and whatever action you output will not be, well,
Yeah.
at best it will be a random action. So yeah, with this kind of setting, it wouldn't really make sense to be doing an offline planner.
By the way, you didn't talk about Gallet, like this mixed cases stuff, or did you? Q-star and V-star realizability and stuff like that.
Yes, I did not. So you could also, okay, I guess it's worth a sentence, at least. So you could also imagine that you have both Q-star and V-star realizability with the same features. It doesn't really matter. Like, you could have different features and you could concatenate them and say they're the same feature.
Wait, the Q-star features depend on the actions, like, okay.
Yeah, like, okay, you could still concatenate them and say, like, for the actions, it's,
Okay.
I don't
Yeah,
know.
you could
It's,
do something like
yeah, it probably doesn't matter. You could, yeah, just say different features. It's fine. But yeah, it's like you could have this kind of a setting. And the super interesting part here is that if you look at the bilinear paper, and they say there's a polynomial upper bound for this, but that only holds for the global axis. Is that how you say it? The global axis? So if you receive all the features in advance for all states and all actions, you receive all the features. You can kind of look through all of them and like look at consistencies, and then anything that you are left to have to check is a polynomial number of things. But if you don't have the global axis and you only have local axis, then it is impossible. So it then is the lower bound, the exponential lower bound applies just by changing the axis mode. And the reason is that, like, there will be there will be states that you basically cannot ever reach with, there's no transition that goes there from the starting state. And those would be the informative states, but you don't reach them, and you will never see them. So, like, there are some caveats with the global planning. Like, you see all the states, and this sometimes matters in ways that you wouldn't expect. It's pretty interesting.
Yeah.
In other, I mean, you could say, why don't we remove the states from the MDP if you can't reach it? And then I will say it is the states, it is the identity of the states in the MDP. If you get that as a set, then that will somehow define your theta. But if you don't get that as a set, then you don't know what theta is.
Yeah.
The lower bound kind of, and it's interesting to see, like, there is a lower bound that works for the local axis, and there is none that could work in the global axis, because there's a polynomial upper bound. So there's really a hard distinction between the two, provided that you can infinitely pre-process the data that you receive, and you only care about query complexity.
Oh, and is there a version of TensorPlan that works in this case, by the way? It's like, do you have to go to the bilinear paper?
For the both Vstar and Qstar realizable,
Yeah.
the bilinear paper is better in that case, right? Because it won't have the a and the exponent. I mean, you can also use TensorPlan, right? But TensorPlan also only uses the local axis, and it doesn't do this pre-processing. So if you have a global axis kind of model.
Yeah, I was thinking about the local axis, and then You have realizability for reachable states.
Mm-hmm. If you have that,
Wait.
then you wouldn't be
Yeah,
able to
then you
use
have
the.
lower.
Yeah, then you have the lower bound. You can't use the bilinear.
Yeah. By the way, in the other part of the literature, which is less theoretical, people are arguing back and forth about this. By introducing these advantage functions and whatnot, and like these dual-headed neural networks, which represent values and action values and advantages and whatnot.
Mm-hmm.
And yeah, so that they've been experimenting with it.
Wait,
And
how's that relevant here with the advantages? Like, what's the relevance with the
so it's
access
like,
model?
so somehow they are arguing that like an advantage-based representation, which is based on representing optimal values and optimal action values simultaneously or in parallel, is advantageous and helps with speeding up things,
Right.
which I was always wondering about, like, how do you argue about that? Because I can't argue just like on a purely statistical grounds.
Isn't there something about the variance of?
Yeah, that's the argument that they always bring up, but
I can't actually make that precise. I don't know how.
I can't make sense of it. I tried. Like, there is no difference.
Like, I guess if you count the variance without like subtracting the mean, so you count like the average L2, then that is larger, and if you call that variance, then you have an argument. But I don't know why that should matter.
Yeah, so the way I was looking at it is that by the time you can learn all these values accurately enough, you suffer the same variance at least as if you were just working with Q star. So they say that, oh, I introduced a Vstar approximation, and with that I'm gonna save something, but like, you're still using the Q star values, buddy. So how do you save anything? I don't know. It's not obvious that you can save with this. But maybe you can, but it's just like, I don't believe that it is based on purely arguing in statistical terms. Maybe, you know, like the Bauman equations nicely play together. So we see that under this global access thing, actually something nice happens, right? Like you reduce, but it seems suspicious because it only happens under global access, which
Yes.
you don't really have or use. So it's
Yeah.
like, it's almost
Only.
a good explanation, except it's not.
Yeah, it only works with the global access and only if you have both Vstar and Qstar realizability. And it seems to be kind of a, as you say, suspicious.
It's, yeah, too much of a corner case. Anyways, I think we should leave it at what it is. Maybe someone here is gonna figure it out why this matters. Okay.
Okay, cool.
All right. Okay, thank you. This was awesome.
Thanks for the opportunity, and I hope I didn't create too much confusion here. So, yeah.
And maybe you come back.
Have fun with doing the open questions.
Right.
Maybe by the time I'm back.
You're retired. You're not going to ruin any of the open questions for the people here.
I mean, I don't know. It depends. You know, if you're fast enough.
Okay. That sounds like a healthy point to start. Point to stop at. Introduce some competitive aspect. All right. Okay.
Okay.
Yep.
See you.
Thank you, Galia.